Okay, brilliant. Thank you. So the mouse wasn't on. So I'm interested, and I have been for some years, in this kind of formal connection between models that can make predictions on individuals. And that tends to be the focus in like AI and machine learning. A lot of it is about predictive models. We have an individual, they walk into the room, we look at some of their attributes. Can we predict, say, a disease risk at the individual level? But a lot of kind of medical science and epidemiology wishes to kind of aggregate at the population scale. What is the effect of an air pollutant on the population, the average treatment effect? And so there's this kind of interesting interplay between, if you've got a model that's really good at doing individual prediction, how can we aggregate that up to a model that is good at doing population scale inference? And what I want to convince you is that those two things are, in a sense, one and the same in Bayesian inference. Is when you're looking at Bayesian probability, posterior probabilities, you're actually looking at statements about predictions on the population scale. And there's some technical papers that back this up by myself and co-authors. So, and I apologize, you just had your lunch, but we're going to need a little bit of probability recap for what's going to come. So 3 essential rules of probability that you will have all been taught at some point. Number 1 is the chain rule. It says any joint probability, the probability of having, say, 2 diseases, can be factorized. You can always factorize a joint probability into a conditional and a marginal, and you can do it either way. A, B can go A given B, P, B, or it can go P, B, A, B, and A. That's rule number 1. Rule number 2 is the marginalization rule, that if you're not interested in B, you can sum over the joint probability in order to make a statement about the marginal probability of an event. Conditional probability, which is what we're often interested in what's the risk of an outcome given some measurements, is formally written as the joint probability divided by the marginal. And then finally, and hence important for this talk, is that so-called Bayes rule, or people call it Bayes theory. I kind of prefer it as a rule because it's just a simple manipulation of 1 and 3. Yeah, once I know 1 and I've got 3, I just substitute in for the numerator here with this equation there. There's nothing controversial about Bayes' rule. It's just a restatement of conditional probability. The controversy comes from using Bayes' rule to do inference, yeah, in medicine or epidemiology. Okay, and so let's just make sure we've got those rules. So here's a joint probability distribution, which we've discretized, and the height, say that this is one variable, say, I don't know, age, and this is weight. And then the heights of the bins would be the number of people that we have of a particular age and of a particular weight. This is a joint probability. The sums of the bins, if I add them all up, they equal 1, because it's a probability statement. The factorization says if I want to know the height, the probability event in this bin here, I just go to the marginal. So first of all, calculate the probability of being on that, say, column, and then given in that column, what's the probability that you lie in that particular bin? Yeah, and so equally, the conditional probability says I now want to condition on a row or a column. Well, if I do that, then the heights of the sums of those bins no longer equals 1, equal less than 1, and that can't be. So we need to divide by the marginal probability, which is the sum of those things. So you can interpret those, all of those rules about probability can be interpreted from that diagram. Okay, let's get kind of going. So Bayesian inference typically uses Bayes' rule for reasoning about population parameters of interest. So we have a parameter theta that we're interested in. We have some data y, and the famous formula says that we have the likelihood function times a prior that's normalized. So up to proportionality, we can remove that numerator. It's not indexed on theta. we have that kind of famous formula, which gives the classical interpretation of Bayes, is that you start off with your prior, you get some data, I have a likelihood function, and I multiply the prior by the likelihood, and then that takes me to the posterior. There's very kind of natural interpretation of, as the information arrives, we update from prior to posterior and then forward. Okay. Bayes' rule, that rule of how we get the conditional probability, is so useful that it gave Bayesian inference its name. But there's nothing Bayesian about Bayes' rule. Yeah? Being kind of Bayesian inference is about a conditional probability statement on a parameter of interest. Bayes' rule is just a manipulation. It's just a theory for connecting a joint distribution. Although it's incredibly useful, and that's why it's like when you say, oh, I Googled it, you mean you searched for something. But Google is such a useful tool that that's become kind of synonymous with searching. It's just the same way why people call it Bayesian statistics is because Bayes' rule is so important for it. And in fact, the formal starting point, and this is going to be the crux of what we want to talk about, of Bayesian analysis is not a prior, but it's actually about a predictive statement, about a predictive distribution. So first kind of proper equation or technical equation, what we've got on the left-hand side is a probability distribution over observables, data. This is a probability, a predicted probability on data, and we write that as a marginal distribution of the likelihood function times the prior. Formally, this is a little bit more than a likelihood function. It's a full probability distribution, whereas a likelihood function doesn't have to be normalized. Here, this has to be a valid probability distribution. From this predictive view, when we look at the task, is to build a predictive model for outcomes. The prior is just a tool. It doesn't have any kind of meaning here in terms of, oh, your beliefs about a certain parameter. This is the kind of direction we're going to go. We're just going to use this, or one would use this purely as a tool in order to plug into this equation with a likelihood function in order to get the thing that you do want, which is a predictive model. Yeah. By the way, any points of clarity or any questions as we move through this, please shout, because I'm aware that we're gonna keep unpicking this onion, unraveling, yeah, through these kind of layers. So the task is to get the left-hand side, which is a predictive distribution on observables, because if we can do this, we can answer any inferential question. It's going to be important. Okay, so let's back out a little bit. So we've got Bayes' rule. If we have n observations, so we've got a data set of size little n, we've got something called conditional independence, which means I can now write this posterior distribution as the product of each individual datum given the unknown parameter times the prior, and it has that form. And it's worth just thinking about that. This is the reason why this is so kind of powerful in a way as a formula is it allows you to write something that you want. You want to be able to make statements about a parameter of interest, which is very hard to think about. How do I characterize that? And you turn it into something which is much more manageable. Yeah, that's one of the reasons why Bayes' rule is so useful, because I've turned this from something that's hard to think about in terms of things on the right-hand side, which are much easier. This likelihood function, I can think if I really knew the parameter, what's the chance of seeing the data that I've actually seen? If this coin was really fair, this coin really had a probability of a heads of 0.5, what's the probability of seeing all of these zeros? Mixture of zeros and ones, yeah, heads and tails. And then you just multiply that by everything you know about the prior probability on that. Okay, so most people can agree on a likelihood function, the kind of sampling distribution for the data, if you knew the parameters. And so the controversy normally sits around this use of the prior. And the other thing maybe just to note is in Bayesian inference, everything you do is model based. That's another note. Everything that we do in Bayesian inference, as opposed to non-Bayesian inference, is using predictive models. Okay. So if you work in Bayesian inference, you often get asked, and often people won't do or think carefully about whether they should do Bayesian inference by thinking about where does the prior come from. You get asked, where does the prior come from? Why should we, is it scientific to introduce a prior? And that's led to a kind of quite considerable effort in the search for so-called objective inference, falling under the field of objective Bayes, with a whole load of prescriptive ways of specifying priors. And it was one of the criticisms of the late David Cox that there were kind of many different flavors of Bayesianism. How to specify the prior? Well, there are reference priors, Jeffrey priors, all of these ways. They're all aimed at some kind of default starting point, to be able to kind of plug into that equation to then update in order to get the thing that you want, which is the posterior distribution on a parameter of interest. Okay. But if we start with Bayes' rule and we have the following formula, some of the kind of foundational questions that we were interested in is to say, well, you've got the prior, and that's kind of, well, I understand what the uncertainty is around the prior. It's your beliefs about theta. And now I update, and I've got this prescriptive formula. I've got this formula on how to update. But what's the source of the uncertainty after the update? I've got a prior. Maybe it's kind of bell-shaped or normally distributed. I see some data. It's now looks kind of normally distributed. But what's the source of that uncertainty? And how do we interpret, say, the Bayesian credible intervals of uncertainty, and how do they relate to confidence intervals? And this is what we're going to go after using a kind of what's called a predictive viewpoint. And this, in the essence, and it might come across a bit unusual, but this is where we're going to go, is the following: is that all uncertainty arises from data that you don't have. Okay, so statistical uncertainty arises from the information that you don't have. That's why you need statisticians. Because if you had all the data, there's no uncertainty. Yeah. So to give a concrete example, suppose you wanted to know what's the average height of people that attend the Dole seminar. Yeah. There is a number, that's a population, let's say it's the people in this room, and there is a true value of that. So if I take a random sample, I do an experiment, I pick out 10 people and I measure their heights. Yeah. Then the uncertainty arises because of the people that you haven't measured. Okay. Because if you measured everyone in the room, you'd know the answer. So in other words, what we're going to do is we're going to make the data that you don't have in the population of interest the focal point of the analysis. And I've written the data that you don't have as going from n+1, the first individual that you don't have, and I'm going to go from that to the total population size. So if you're interested in what's the effect of air pollution in the UK, and you measure 10,000 individuals, then the people that you haven't measured is the remaining people in the population. Okay. And we're going to model the data that you don't have rather than the data that you do have. And what we're going to show is that inherently, this is what Bayesian inference is doing. So when you're doing Bayesian inference and you're presenting a posterior distribution, inherent to that is a predictive statement about the population that you didn't see. So uncertainty in population of parameters, all the uncertainty flows from the missing data. Because if you had the missing data, there'd be no uncertainty, you'd know the answer. And we're going to kind of connect these to this rather trivial statement. We're going to formalize it and show that it can lead to kind of new ways of thinking about Bayesian inference. Okay, so back to our kind of probability kind of recap is we start with a joint distribution over the parameter of interest and data. Now, what we said is we can always factorize a joint both ways. We can go theta given y, p of y, and we can go y given theta, p of theta. Yeah, so that was rule 1 in our probability recap. And all I'm going to do now is I'm going to take this p of y and I'm going to divide through and move it to the right-hand side. And that gives me Bayes' theorem or Bayes' rule. Okay, and if I move p of y, if I divide through, then I isolate the thing of interest, which is the posterior. That's the thing I want. Yeah, so I just divide through by the marginal for y. But there are other ways to get the posterior. This is a really good way of getting the posterior. That's why it's called Bayesian statistics. But there's other ways of obtaining that posterior. And this is the way that we're going to go after it. We're going to directly target this posterior. So this says, given my data and a parameter of interest, we're going to use an approach called data augmentation to expand the posterior distribution to include the data that you don't have. And this might seem like you're wondering why on earth are you doing this? Hopefully it will become clear in the next couple of slides. So, so now I've got a joint posterior over not only the parameter of interest, but all of the remaining data that I didn't have. So if I wanted to know my inference on the heights of the people, I've got the data that I've got. I'm just going to pull here. And now I'm going to expand my posterior to include the unmeasured data from people from the missing population. And just for notation convenience, I'm going to call y-obs the data that you've seen. Y-miss is the remaining population, n plus 1 to whatever this population size. And then the complete data is the stuff you've seen and the stuff that you don't have. And just to note, if you had all the data, you'd have all the answers. Okay, so now we've got this rather odd object, which is huge because it's got the data that you didn't have. And we're going to work with that object to get back to this thing, and you'll see why this might be useful. Okay, so we've got, maybe think about this one here. This is using the actual kind of notation, but this is where we're going. I told you we're going to augment the posterior to get the missing data and the observed data. And now using my rule R1, I can pull this missing to the right-hand side. And I get this. This is just from rule 1. But now I'm going to take this joint distribution and I'm going to write it as a posterior given the complete data and the missing data given the observed. And this is the key. This is the key equation to where we're going with this idea of predictive inference. Yeah. Because once you've got this, you can get back to this posterior through this marginalization trick. Yeah. But we're going to use this equation to characterize our inference. Okay, so we expand out the joint distribution to include data that we don't have, and then we marginalize out the data that we don't have to get back to the target of interest. And that we're going to show an example of, or talk through an example of why that might be kind of interesting. Note that equality holds for any Bayesian posterior. So anytime you see a paper that gives you a posterior distribution over a parameter, it has this implicit decomposition or has that equality. This is, I haven't done anything other than use the rules of probability that we looked at on the first slide. Okay. Well, if I'm going to use this object in order to do inference, we've got two components. The first is the posterior distribution arising if I had all the data. And the second thing is a predictive model for the unmeasured data. Yeah, so that's given the data that you've got, can you predict the data that you don't have? Well, the posterior, given all of the data, has got no uncertainty. Yeah, if I've got all of the data, then I know the parameter. Yeah, my heights of people, if I had all of the information, if I'd measured everybody, there's no uncertainty left. Okay, and we can just write that as an implicit statistic. Yeah, so this posterior distribution, given all the data, is just a statistic of your complete data table. So if you imagine your Excel spreadsheet, imagine there was really a row in your Excel spreadsheet for every person in the population. You've only got the first little n rows filled in. If I filled in all the remaining rows, you'd know the answer. Okay. And that's in the kind of foundations of Bayesian inference. That's the lurking parameter of definity. Okay. And now we can see that the Bayes posterior has these two components. Any Bayesian posterior can be represented in this form. There's just the parameter that you would pick off if you had all the data. If you had a complete Excel spreadsheet for every individual in the UK, then you pick off your parameter, your epidemiological parameter. But now I've got a prediction task. Yeah, which is given the data I've got, I need to fill out all the rows for every individual potentially in my population. But what we can see, because every posterior that you ever come across has this decomposition, because this is just a rearrangement, yeah, from the rules of probability. Bayesian inference is inherently predictive because every posterior has that decomposition. That's in contrast to maximum likelihood estimation. So maximum likelihood estimation is not predictive. Yeah, if we fit a model by maximum likelihood estimation, that's for estimating parameters of distribution. It's a different task to prediction. And what we're seeing here is that in Bayes, whilst you think you're doing an inference task, and you are, implicitly you're making a predictive statement on the data that you don't have. And because there's no uncertainty on this for this component, all of the uncertainty in here flows from this prediction. That's what I meant by all of Bayesian inference, all of the uncertainty in the posterior distribution. The source of that uncertainty is the missing data. Well, at the moment, this is just kind of, a kind of mathematical formula, but can we actually can we compute with this? Yeah, we know how to compute with Bayes' rule. We do MCMC or we do conjugate updates. How might we compute with this representation? And we can do that through, and I kind of hinted at it, this data augmentation approach, which again we're going to have to unpick. But trivially, and when I say trivially, someone could write this down, but of course the devil's in the detail of how you would do it, would be, suppose I can sample all the missing rows in my data table using this prediction. Well, then I'd have a complete data table. I would just pick off the parameter of interest, the average treatment effect, the average height, the total height, the weight, whatever. And then I would repeat it in an imputation. I'd then throw that data table away. I'd then fill out a new data table using this predictive model. And then I'd pick off the parameter and I just repeat that over and over again. And I'd get a bag of samples. But of course, this requires the ability to simulate the missing data. That's the problem. It's like, oh, I've got to fill out from the joint distribution. I have to fill out the complete data table. So here's the algorithm for how you might fill out the complete data table. So imagine you've got a clinical trial. You've measured n individuals. We can make this task in the following way. I'm going to first of all take a univariate predictive model. So this just has to predict one individual, the next outcome for the next patient. Okay, and it has to be a generative model. I need to be able to simulate that next patient or that next sample and make a prediction on it using the data that I have. This is now a synthetic sample because it's been generated by the model. I'm now going to plug that back into the training data. And I'm going to update my model. So my model now has n real datums in there and one synthetic datum that's been actually generated by the model. And then I'm going to repeat that. And I'm going to sample the second data point, given the real data and the first one that's sampled. I'm going to put that second data point back in. And I'm going to keep going. I'm going to make these predictions, update. Well, when I say prediction, I'm actually going to sample from the distribution. I'm going to simulate an individual. Then I'm going to put that individual into the training data set and treat them as if they were real. Keep going. And in that way, if you imagined your Excel spreadsheet, you would fill it out one row at a time, but the training data is increasing in size. At the end, for very large N, I've now got a complete data table, and I can just pick off the parameter of interest. And that parameter entails n real and capital N minus little n synthetic. Suppose you're interested in the average of the outcomes, it would take this form. This theta is a random variable. It's random because these capital Y's are random. But the real data is fixed. The only random component comes from the synthetic data. Well, if theta is random, it means it's got a distribution. Okay. If you use this, your prediction as a posterior prediction from your Bayes model, you've done your Bayes model, and you now you just run this algorithm. What you will find is that having done all this extra work, you're back to where you started from. The thetas that you sampled come from the posterior distribution. As n gets very, very large and subject to some technical conditions. Yeah. So this algorithm here shows how you go from a predictive model to the posterior distribution. And you can do this, and here's an example of it. So what we did is you get some data. We took just like n samples. We sampled the data from a normal with some unknown theta, which we plugged in. We suppose that there was a Bayesian prior on the unknown mean. Yeah, from the data that we generated, I think that the mean was around 1.75. So that was our empirical average of the data that we generated. And then we played this game. We said, right, now we're going to make the Bayes model make a prediction. We take the predictive point, we generate a new datum, we then put that back and we update as if it was real data, and we keep going. And what we're seeing here is the sample paths of the means, the averages. And what you see is that to start with, they're kind of quite variable. That's a consequence of like the root n you get on the information, is that when you've got less data, any new datum gives you quite a lot of information. When you get more and more data, any new datum doesn't give you much of an update. Yeah. If I look at these sample paths, they're random. because the data I'm generating are random. If I now pick off these parameters at the end and compare them to the Bayes posterior that actually I didn't need to go and do this simulation because I knew what the Bayes posterior was because it's a conjugate, I get equality up to some level. Hey. Oh, sorry, kernel density estimate. So this is a way of just turning these, I get a bag of samples here, and I want to compare them to the true Bayes posterior, which I know is normal. But essentially, if you think about these as Monte Carlo samples, you would then construct intervals from. Okay, so to implement that approach, I need a predictive model that I can sample a new unit from, and I need to update the predictive model, and then I need an estimator. Like, the key point is traditional Bayes dictates the form of the predictive model. In fact, that was on one of the initial slides, yeah, that the focus is on the joint predictive. And if you're using this construction, you don't need to go through all that simulation because you'll end up where you started. But the issue here is that this opens up different forms of predictive models to allow you to do Bayesian inference in more general settings. For people who work on Bayesian adaptive clinical trials, this will be very familiar territory. Like early stopping, what's the probability? You kind of run your simulation forward and look at what would happen at the end of the trial. What we're seeing is traditional Bayesian inference is no different. It just keeps going. There's no end to the trial. And your analysis with your data in hand is akin to making a statement of what would happen if I just kept the trial open and I accumulated more and more data. That is the inferential statement that you're making, or one way of interpreting the inferential statement. It's a Bayesian inference is a predictive statement about what would happen if I collected more and more data. And that's different, of course, to the uncertainty quantification that comes from non-Bayesian, like classical, well, frequentist measures. So traditional Bayes, you specify a likelihood and a prior. Here we're specifying an estimator. What are you going to do if you had all the data, and a joint predictive model? The thing is, I mean, this, as I said, the actual underlying, the equation is just a trivial data augmentation approach. But the reason why I think most of stuff is done with Bayes' rule is because it's simple. And 40 years ago, say, when Bayes was starting to take off again, the idea that you could build a predictive model for the whole population, given a subsample from that population, seems totally unfeasible. But now, with modern compute facilities and a whole load of work in like generative AI and synthetic data generation, this is no longer out of reach. So our argument is that actually we can obtain these predictive type of models nowadays. That's not to say you shouldn't use a prior. All I'm saying is that a prior isn't necessary. Now, that's quite a controversial statement, but you don't need a prior to do Bayesian inference. Yeah, you need a predictive. We've just shown this is conditional on the observation. Yeah, there's no prior involved. Now, you might want to use a prior in order to get this thing, but you don't have to. Yeah, the essential element of being Bayesian is the predictive statement about the missing data, not the use of the prior. It also shines light on the difference between frequentist uncertainty in confidence intervals and Bayesian uncertainty in credible intervals in the following manner. We have an estimator of interest. So you have some estimand. I want to know the average treatment effect. Yeah, we can think of frequentist intervals as being constructed in the following way. I've got my estimator, my estimating equation, say it's just taking the mean of some outcome. And frequentist uncertainty considers what would happen if I repeated the study. If I repeated the study, I get another sample of size n. I would put that data into my estimator and I'm likely to get a different value because of the uncertainty in repeating the experiment. And this is by definition the frequentist measure of uncertainty in a confidence interval. Or if I was to repeat the study, what would happen? And if I was to repeat it again, what would happen? And the way you would do that is you would sample studies of size n. Here's the Bayesian uncertainty. We've just derived that. It always conditions on the data that you have. Yeah. And it treats the data that you don't have as the random component. But it puts them on equal footing. So sometimes you hear people say, oh, Bayesian inference treats the data as fixed and the parameters random, and frequentist treats the data as random, the parameters. I don't believe that. They both have the same estimand. They both have the same target. They both use the same estimator. It's just the uncertainty for Bayes flows from the missing data. Yeah, frequentist uncertainty is indirect. This is talking about the finite sample variability of the estimator, whereas Bayesian uncertainty is on the prediction for the missing data. Both interesting in their own right. Not saying one is better than another, they're answering different questions. I'm aware of time. I'm going to talk you quickly through a bootstrap example because I think it's illustrative, because most people will have come across the bootstrap, and then we can look at its Bayesian interpretation. And then I'm going to jump quickly to how we use this technique recently in large language model understanding. So the bootstrap is a general method for constructing confidence intervals. And the bootstrap has the following algorithm. You start from the empirical distribution, that's your data table. So that would be hypothetically, your Excel spreadsheet. You've got n samples. I just go and grab another n. I just pick one at random and put it into the n+1 slot. Then I go and pick another one from the 1 to n and put it in, and then I put it in and put it in. And I generate myself a new data table of size n, little n, by picking with replacement. So pick one out, copy it, go and pick another, but I always keep the original. Then I calculate my estimate, say a maximum likelihood, and then I repeat. And if I do that, I get bootstrap confidence intervals. Well, what's the Bayesian analog? Well, we've just seen what we need to do. What's interesting is that we're going to start from exactly the same point. So there's no prior is going to come into this. So this follows formally something called the Blackwell and McQueen Pollier-Earn representation. It's got a rather grand name, but of this, which is we're going to start from the same thing. I start from my data table. I'm going to choose a point at random. I'm going to copy that into the n+1 row. And now I'm going to choose another sample, but I'm going to update. So in the Ephron bootstrap, there was no updating. I always pick from my original n. So the Bayes, because we want a joint, we're going to update that. Now n+1 is also in the training data, so I can pick that. So now I've got a choice between 1 to n+1. Copy that, choose one, put it into the next slot. Now choose from 1 to n+2. Copy it, choose, and so forth. And in this way, I'm making predictions by sampling the data table that I've currently got, filling it in, and then updating the data table. And at the end, I've now got a very large data table. I calculate my statistic. If you do that, that will give you a valid, in fact, it's a Bayesian non-parametric measure of a credible interval on theta. Yeah, it's a valid, and it starts from the same point as the non-Bayesian bootstrap. No other information going in. It's just this one is making a joint predictive statement over the missing data, whereas the previous one was saying what's the finite sample variability. Okay, I've got an example for that now on a linear regression, which I'm going to skip over because I want to spend the last 5 minutes talking about how we've used this predictive notion in trying to get an understanding of large language models, which is fairly kind of hot topic at the moment in AI and ChatGPT and all the other variants. So it's a little bit of like step back. Where we've got to so far is this idea that if we predict an update and predict an update, we can get to Bayesian inference through this just kind of machinery without having to specify a prior, if we've just purely got a predictive machine. One thing we know about running that predictive machine for a Bayesian model is something called a martingale, which essentially says, imagine this Excel data table. I've got n samples. I run it forward to complete, then I repeat the whole thing. I get another data table with the real data. I run it forward. If I then look across all of those data tables at any row, the jth row, the predictive distribution of the jth row, on average, will be the same for any row. And the reason is you've got no new information. All of the real data is contained in the first n rows, which is your conditioning on. And formally, what this means is that this predictive distribution forms something called a martingale from stochastic process, which means in expectation, there's no drift. If you were to see drift, you're somehow introducing information into this system when all you're doing is you're asking it to predict and then feeding its own prediction back into itself. That's something that you would not want for if the data is something called exchangeable. So if the rows in your original data table had no meaning, the fact that I call you patient number 1 and you patient number 2, it doesn't make any difference. So that was just an arbitrary label that I had in my data. So if we observe drift in these predictive distributions, then there's some notion of incoherence happening. And what we're going to do is we use that in our to query large language models. There's an interesting emerging discipline now in the science of AI, which is the following. It says, just as biology emerged as a discipline to try and understand what was happening in organisms, there is an emerging discipline on the science of AI, which is they've built machines which internally we do not understand. So how can we start to build experiments that allow us to understand what these things are doing? And this falls under this kind of category. So we've got like LLMs, like ChatGPT. There's a lot of interest. One of those is in this notion of in-context learning, which says if I give some LLM some, say, patient data and then ask to make it a prediction, can it do? Could I use an LLM to make me a prediction for a medical diagnosis? Well, one of the problems in that is, how do we know whether it's doing something sensible? So I can look empirically, I could say, well, the LLM, it seems to be doing okay. I give it some data, I look at how well it can predict or I can see how well it can do diagnosis, but you don't know what the model is doing. We don't know how it was trained. Even the people in the organizations don't know what background information is doing, because it's like large scale information gathering off the web. We don't know how the model's really making predictions. Some people have argued that LLMs are performing implicit Bayesian reasoning. It kind of makes sense. Are they conditioning? And so what we thought is, well, let's try to check this out. We know you've sat through this lecture, you know something about Bayesian inference. It makes these predictions and we update, and we should get back a Bayes posterior. So we took a bunch of LLMs, ChatGPT, 4, Llama, and Mistral. And what we did, this is my daughter said, oh, you're a statistician, what do you do with your LLM? You ask it to toss coins. It's like, oh, Dad, Like, you know, you could ask it to do poetry in the form of Shakespeare, or but as a statistician, we get the LLM to toss a coin. Yeah. And so we give it like this. Dear ChatGPT, you are provided with independent, identity distributed tosses of a coin, which with flips 1 with probability P, where P is unknown. Here is some outcomes. Give me the next outcome. We just asked the LLM to toss a coin, or we could do something a bit more. We give it some background on the disease, and we give it some patient data, and you say, what's the diagnosis for the next patient? Now we can play this trick. We don't know what the model is, but we know if underneath the hood it's doing Bayesian inference, I know what to do. I can get it to toss this coin, and now I can recall the LLM. But now I feed it back its own prediction. Of course, it doesn't. I'm kind of anthropomorphizing. It doesn't. The algorithm doesn't know that I'm feeding back its predictions back into the LLM. But we can do this recursive. We get it to generate. We feed the token back in. We get it to generate. We feed the token back in, and we can look at what happens. And we can look at what happens on average. And on average, we would expect no drift. Yeah, if the predictions drift, then we know something's going wrong. Yeah, and the thing is, it's a bit unremarkable because these models have been built for natural language processing. So natural language is not exchangeable. The order of the words matter. Yeah, but people are using these models in contexts like this. So part of this work was just to flag to people, just be careful. So we asked to generate the LLM to generate a new sample. We then feed that back into the LLM, and then we prompt it for another answer, and we just repeat that. And what happens is you see something like this. This is on the coin toss. So we gave it an unfair coin, I think with probability 0.3. Then we get it to toss the coin and keep going, and some go up and some go down. And to start with, everything looks okay. There's a little bit of drift. But what we've seen is at some point, it tends to go into a different mode. A lot of the LLMs will then just go up and just predict ones and just predict zeros. And so when we look at that, this is the short scale behavior of LLMs. They look okay over a finite horizon. But when we look over a longer distance, we get this very uncertain behavior. And this kind of introspective kind of hallucinations. They're kind of, if we really wanted to anthropomorphize, we'd say kind of by talking to itself, it's kind of creating information. That shouldn't happen. Yeah, that violates the kind of what we would want from an inference process. So you just have to be kind of careful in using LLMs in the context of exchangeable data. Okay, last slide, sorry. So what we've done is we've taken a predictive viewpoint of Bayesian uncertainty, which looks at the missing data, model the missing data as the starting point. This shows that to be Bayesian, you don't need a prior. That's a bit controversial, but what we've seen is you just need a predictive model, which is conditional on the data that you have. It shows that there's a close link between Bayesian inference and the ability to simulate observations. And I think that's another nice link into kind of modern AI, is that we know that modern AI is getting extremely good at generating synthetic data. It also highlights the kind of close connection between frequentist uncertainty and Bayesian uncertainty on an equal footing. And we got some additional work. And thanks for listening. Thank you.